Okay. Okay, great. So here we have the expression, and here, this is the expression for equilibrium constant for the reaction of H2O and CO to produce hydrogen and CO2. You can tell from this one that these are the reactants because it's always products of the reactants. So when you get a K expression, you can tell which are the reactants and which are the products. The products are always on top. The reactants are always on the bottom. So this is the reaction of H2O and CO to produce the products of hydrogen gas and CO2. Now, if we take experiments, the experiments either one or two, we can actually substitute into here. So what we're doing is taking these concentrations here and placing them into the equilibrium constant, and we can calculate the equilibrium constant. For experiment 3, let's look at experiment 3. They had different concentrations than experiment 1. They had 0.02, the same concentration of water, and less concentration of CO, and they have to start with initial concentrations of H2 and CO2. And yet they found the equilibrium is a new point. So none of these concentrations in equilibrium of the experiments match any other one, any of the other experiments. But then nonetheless, they are at equilibrium, and that equilibrium can be placed into the equation, like in this case for equilibrium 3, and you still will get the same equilibrium constant. So that's why it's called the equilibrium constant. The only thing that will change the equilibrium constant is going to be a change in temperature. So the concentrations, as you can see, do not change the equilibrium constant. In general, the expression for equilibrium is going to be of this form. And in this case, we don't need to know that these are elementary steps. They could be a whole set of 2, 3, 4 steps, reaction steps, elementary steps. But the overall stoichiometry of the reaction is going to give us the exponent. So A, notice here, is the exponent of A. And B here is the exponent here. And C here becomes the exponent of C, and so on. So those exponents are going to be important because they will make a big difference in your calculations if you actually forget to place them. The same thing can be done for Kc and Kp. And Kp is going to be based on partial pressures of each of the components in the gas. So you can calculate it from molarities, you can calculate it from partial pressures if you are dealing with gases. Molarity is usually in solution, but also is fairly common in gases as well, calculating molarity of the gases. So pressures can only be applied to gases. Okay, so here we have different reactions, and let's number them. 1, 2, and 3. So for reaction 1, the K is a very large number, 10 to the 81. That's a huge number, which means that this reaction is favoring the products, because the K, there's not much space for me to write here, but let me put it here. K is equal products over reactants. And being products over reactants, then the products are, the products have to be very large with respect to the reactants to give me 10 to the 81. It's a huge number. If Avogadro's number 10 to the 23 is huge, this is unbelievably huge. Which means that when you actually take hydrogen and oxygen and make them react under certain conditions, they're going to form water. And the water is not going to go back to hydrogen and oxygen very easily. So in this case, the products are favored. Now, when we look at equation 2, this is 10 to the minus 92, excuse me. So this is hugely on the other end of the spectrum, meaning this reaction is not going to happen and go towards product that much. So if you have CO2, it's very unlikely that it's going to become carbon monoxide and oxygen gas. So the equilibrium lies towards the reactants. And for K24, that's telling us that the equilibrium, it still favors now still the products, but there's going to be still significant amounts of H2 and CO. So it's not that the ratio is not like 10 to the 80 or 10 to the minus 9. Okay. Okay, so let's look at the next practice exercise for the equilibrium constant. So we have this reaction. This is the formation of ammonia. And ammonia is a very critical compound in terms that ammonia is used for a lot of things in industry. It can be, usually the main use is going to be fertilizers. And so today we cannot do without fertilizers in our agricultural practices. Otherwise, we will not be able to feed the 7 billion people that are on Earth already. So this is an important reaction, and it takes nitrogen from the air and hydrogen, which actually is nowhere on the planet. It needs to be produced. And so hydrogen needs to be produced and reacted with nitrogen, and usually about 500 degrees centigrades and 14 atmospheres pressure. So it's a pretty high pressure. And then you get this reaction. You form ammonia, which then it can be used to produce other many chemicals, not only fertilizers, but fertilizers in terms of bulk. Most of the ammonia that is produced is turned into fertilizers. So this is calculated the equilibrium constant, the following system 500, yeah? That's the temperature in which it is formed. And they're giving us the amounts. So they're telling us that the nitrogen concentration is such, the hydrogen concentration is such, and the NH3 concentration is such. So they're giving us a concentration. So we need to actually just go ahead and write, to start to do this is to be able to put those concentrations into the law of mass action for this reaction. And the law of mass action for this reaction is K is going to be equal to concentration of NH3 squared divided by the product of concentration of N2 to the power of 1, concentration of hydrogen, H2, cubed. So notice what I have done here. I've taken the products as the numerator, which is here, and the reactants as the denominator. So these guys here, up here, and is the product of them, not the sum, but the product. Although here's a plus because it's the chemical equation. Mathematically, when you do the law of mass action, you're going to multiply. And then now that you have the equation, then you can substitute these values into the equation and calculate a K. Okay, so let's do that. So here's the K that I wrote before, and here's the substitution. Do not forget the exponents, because that's a common thing. Most people go up to this point, and when they substitute, they forget to put the exponent. They're so concentrated into putting the concentrations into the right places that they forget the exponents. Once you have done that, you can multiply and operate that mathematically and obtain a value, 0.0603. So it looks like this is less than 1. And if you look in here, look at the concentration of NH3 is 0.15. concentration of the reactants is 0.7, and this is almost 1, which means that the products are not favored for this reaction, right? And that this K less than 1 means reactants are favored.
I have a question.
Yes, please.
So, if the products are favored, that essentially means more of the reactants are used up, right?
Correct, correct. In this case, the reactants are the favorite. You see, these are the concentrations on equilibrium, and the concentration on equilibrium are larger for the reactants than for the products. So in this case, the reactants are favored.
Okay.
Yes. So K, actually the value of K can give you an idea of how much the reaction is going to go toward it. Now, the only way that you can change K is by increasing the temperature. And it looks like this is already 500. So they have to do some, what they do in the industrial process is they take the nitrogen and the hydrogen, pass it through the column. This column is like the as tall as a two-story house. So this is the column. They have a catalyst actually to speed up the reaction, and they pass the nitrogen and the hydrogen, the mixture through here. And here they're going to get NH3, but mostly N2 and still hydrogen. Now, ammonia actually condenses. So I think at minus 15, minus 20 degrees centigrade, it will condense. So what they do is they pass it through a cooler. And so the ammonia condenses as a liquid, and it can be separated from the gas just by gravity. And then the gas is recycled again with a stream of nitrogen and hydrogen that is coming again. And it passed again through the column. So that's the way that ammonia can be produced. And the hydrogen is not wasted because this will reach equilibrium as it goes through the column. There's a catalyst that makes it very fast. And then when they come out, oops, here's my finger. When they come out, the ammonia can be separated and the nitrogen and the unreacted nitrogen and hydrogen sent back again through the column. And so that way they can have a new equilibrium, because if they wouldn't separate the NH3 at this point, then the NH3 will go back in here and it will be an equilibrium already. So that's how they are able to harvest the ammonia from the system. Okay. So the equilibrium, the K being less than 1 favors reactants. Okay. When the equilibrium is in the gas phase, we are going to use the ideal gas equation. So PV equals nRT is the ideal gas equation. So if you didn't see it on Gen Chem 1, this is the ideal gas equation, and we are only going to use the ideal gas equation. This one, PV equals nRT. So P stands for pressure, V is for volume, N is for number of moles, R is a constant, a gas constant, and T is the temperature in Kelvin. And that's where most people make a mistake of using it in centigrades. It needs to be converted to Kelvin. Okay, so here they have actually solved this equation for P. So P is equal to something, something. Now, this N over V is the number of moles divided by the volume. If the volume is expressed in liters, that means the number of moles divided by liter is molarity. So we can think about this as P equals molarity times RT. Okay. So we can do calculations to calculate the pressure if we know what the molarity of the solution is. So we can go from concentrations to pressures by using this expression here. where R is the gas constant and T is the temperature in Kelvin. And then we can calculate pressures and calculate a Kp rather than a Kc. So Kp and Kc are going to be related through this equation here. I'm not going, even if it's here, I'm not going to go through the derivation of that, but you can derive it as well. So Kp is going to be equal to Kc, concentration times RT. If you remember this one, or this one, you know that pressure is equal to molarity times RT. So Kc is going to be, Kc is molarities and times RT. Now you have a delta N. What is that delta N? Delta N is the number of moles products of the product minus the number of moles of the gases in the reactant. So that is something you need to look at the balance equation and figure out what is that delta N. And so RT is going to be to the power of delta N. The R constant, if you have steady gases, this is that's the value of the R constant. And so that's the one you need to use. And the temperature again in Kelvin. Don't make a mistake to forget and put it into centigrades. So you can relate Kc and Kp using this equation. So you don't have to go through all these calculations. If you have the Kc, you multiply by RT to the power of delta N. So let's go into this. So let's calculate the delta N here. The delta N for this reaction is going to be equal to, because there are two here, minus is products minus reactants. So final minus initial. So it's going to be 2 minus 1 and 3 is 4. So minus 1 plus 3. So the delta N is going to equal to minus 2. Okay, so if you have the Kc for this reaction, we calculated it here. So this was based on concentration. So when did you see this one, this expression here? This is concentration of A in molarity. So this is the Kc. So we have the value of the Kc. We can put it into here and multiply by RT to the minus 2. And that will give us the value of Kp. And vice versa, we can do it as well. If we know the Kp, we should be able to calculate the Kc. Okay. Let's look at a second exercise on the law of mass action. So this is the reaction by which actually fertilizers are still going, still made, because you will say, well, I told you that NH3 is used for fertilizer. That is true. But in the process of converting ammonia into, if you add ammonia directly to the soil, which we do, especially for corn, what happens is the ammonia itself is the source of nitrogen for the plants, but ammonia itself cannot be absorbed by the plants. So what happens in the soil is there's bacteria and there's a chemical reaction through which ammonia, NH3, is transformed into nitrogen, into nitrogen oxides and eventually turn into nitrates. And it is the nitrates that the plants are able to absorb. So in this case, it makes more sense if you are using NH3 as a fertilizer to actually transform it into a nitrogen oxide or into a nitrate. And the first step in converting it into a nitrate is to oxidize it. So this is done again in industrial scale. And this is, there is a reactor that looks like a funnel that has been inverted. So the wider end is on the bottom, and then there's a funnel, like another funnel, like two funnels that have been, one is upside down and the other one is going on top, or that upside down is going on top of a right side up funnel. And you open that, and it has a diameter of about, I would say 8 to 10 feet. And it has a mesh, a metallic mesh. And that metallic mesh is made out of platinum. And that's the catalyst for this reaction. So this reaction is catalyzed through platinum to be able to to transform ammonia into nitrogen oxides, which eventually lead to nitrates. And so the transformation of NO2 into nitrates is not that complicated. But this one here, this reaction here, is the one that is challenging. So there's a precious metal, platinum, that is used to do that. And actually, there's such a flow of gases that are put. So these two reactants are put through that mesh, and the mesh is very thin, and yet it has to convert about 90% or 95% of all the ammonia and oxygen into nitrogen dioxide and water. And as the flow goes by, it spends only a fraction of a second on the platinum. And therefore, the reaction has to be very fast. And platinum is a metal that actually catalyzes this reaction. It makes it very, very fast. Okay, so they're asking us to write the equilibrium constant expression for Kp. So when we're saying Kp, the P stands for pressure of the gas. So we need to look at all the components that are in the gas phase. And those components are the ones that are going to be in the expression. So in this case, all of them are in the expression, and the expression is going to be products, H2O, product, NO2, to the power of 4, and to the power of 6, divided by the pressure of NH3 to the power of 4, and the pressure of O2 to the power of 7. So it's exactly the same approach that we did for the KCs, but this in the KP, we're talking about pressures. So that is also an equilibrium constant. It's different than Kc, and we learn how to convert Kc to Kp by multiplying Kc by RT to the power of delta N. So in this case, they're asking us to write the expression for Kp, and so the expression for Kp needs to be done in using pressures. And not concentrations. Okay, so just pay attention for the K, whether it's Kc or Kp. Both are equilibrium constants. Okay, so let's look at the equilibrium constant for gases again, another exercise. Okay, they're saying that PCl5 actually decomposes into PCl3 and CO2, chlorine gas. I think we're missing it. Looks like we're missing the slide, but that's okay. So we can convert Kc into Kp by using this expression here. So we have the value of Kc, we have the value of R, check mark, check mark. We have the temperature, yes, but we need to take 425 plus 273 to make it Kelvin. So don't forget that it's Kelvin. And the delta N is products. So what is the delta N? It's going to be 1 plus 1 is 2 minus 1. So it's going to be 1 plus 1, products, minus reactants, 1. That is going to be 1. So if delta N is equal to 1, then it's going to be Kp is going to be Kc times RT to the power of 1. So times RT. So here's the gas constant. Here's the temperature in Kelvin. And here's the calculation of the delta N. So once we have that, then we can use the equation to say that Kp is equal to Kc. Here, Kc I t to the power of 1. To the power of 1 is really just, we don't have to do anything. We just multiply those three numbers. And the result is 229. So the Kp value is 229. So notice that in both cases, the value is greater than 1, whether it's Kc or Kp. And that means that the products are favored at equilibrium. So if you have the system at equilibrium, you have more products than you will have reactants. Yep, the reaction favors products. Now we're going to look into how the K actually relates to when we actually change the order of the reaction. So we have been had another half an hour, so let me stop the recording.